Not naming names though now because now we're actually recording. All right, we are going to do a little numerical investigation. I have a triangle right here. And note our convention that we talked about for labeling sides and angles. So this is triangle ABC with capital letters. And I have my geometry software here tells me the angle. And we're going to keep all the accuracy we can. Angle A is 42.46. Angle B is 79.46 degrees. Angle C, 58.08 degrees. And we have our three side lengths. Side A is the side across from angle A, and you have its measurement. It doesn't matter the units. Side B, you have its measurement. Side C, we have its. You guys can just jot those into your table. And we're going to do a little numerical investigation here. All right, I am going to do it too. These numbers are new for me. These different ones every year. So 7.05, 42.46 degrees. 10.27, 79.46 degrees. 8.86, and I thought I had it, 58.08. Got it. Okay, but would you guys agree? Definitely not a right angle triangle, right? This is called an acute triangle. All the angles are acute. They're all less than 90. So definitely not a right angle triangle. We'd like to not have to use SOHCAHTOA twice if we don't have to. So can we find some kind of relationship between all the sides and angles that will help us? Yes, we can. Can you guys, for each of these pairs, can you take the side and divide it by the sine of the corresponding angle? Those of you guys who have a display calculator can just pretty much punch it in as you see it. 7.05 divided by the sine of 42.46 degrees. I'll squeeze this in here. So I got about, I'm just going to go to two decimal places, about 10.44. About 10. Do you guys get about 10.44? Can you guys repeat that for the other two pairs of sides and angles? I'm not going to write this down this time. I'm just going to do the calculation. 10.27 divided by the sine of 79.46. About 10.4. If I round to one decimal place, 10.45. If I just chop off the decimal, about 10.44, I'll just say about 10.45. I'll round correctly. Interesting. How about the third pair? If you round to the nearest hundredth, about 10.44. Did you guys get that as well? I mean, let's think about it. We got the same number for each ratio, about 10.44. Have we possibly discovered some new special number in mathematics, like pi? A number that is inherent to all triangles, like 10.44. Are you guys convinced with this triangle, the ratio of a side and its corresponding sine angle, it's about 10.44, right? You guys convinced? But maybe I cooked the books, right? Because for all you know, I could have pre-made this triangle ahead of time, knowing exactly what was coming. So let me randomize this triangle. So just to convince you that everything's completely random, we're just going to go for a ride, and new spot. And then we'll take B for a ride, put it down here, and we'll take C. We'll take C. There we go. We over here, back here, and let's go right there. All right. Completely random, brand new triangle. I wonder if we'll see this special 10.44 appearing again. That'd be pretty neat if we found some new special number inherent to triangles. Will those ratios still be the same? Will we get something different? It's a completely different triangle, but it's an acute triangle. I'll let you guys get those values and find those three ratios, and let's see what happens. All right, I'm going to come along for the ride here. So 8.28, 65.34 degrees. Yes, I got that right. 8.8, 75.03 degrees. 5.81, 81, and 39.63 degrees. I'm excited. Are we going to get this special number again? I could write a paper and become famous. I could, like, my subscriber count will jump from like 125 to like 140. Okay, kind of sad noises. I got 9 points to 2 decimal places, 9.11. How about you guys? Okay. Boo. Well, what's the ratio? Might as well keep going. What's the ratio for this one? 75.03. Okay. Also about 9.11. This is becoming interesting again. Aha. Also 9.11. Hopefully what you guys noticed, no, 10.44 was not a number inherent to triangles, but within each triangle, every triangle, this ratio of a side to the sine of its corresponding angle produces the same number no matter what the triangle looks like. Remember, I randomized that one, right? You guys convinced? This relationship is called the sine law. Now, I did kind of spoil the fun earlier. I have proved the sine law over here using a generalized method from the warm-up. You guys never have to reproduce a proof of the sine law. However, if you're interested, it's not the pick. It is nice to know where it comes from. But yeah, hopefully you're convinced. And in today's lesson, we're just going to, first we'll generalize and state the sine law, but then we just got to get used to using the sine law and its ins and outs, what we can do with it. So let's proceed. Summary, the sine law. The sine law says that if you take a side in a triangle, now we're using ABC here, generalized on the right. If you take side A and divide it by the sine of angle A, you get the same ratio no matter what side angle pair that you use. That's what we just showed. There is an alternate version of the sine law. It's the same sine law, though. We could have actually taken the sine and divided by the side length. We would have just got some very tiny decimal numbers, so I usually prefer to investigate the first version. But this is true. And this is true. This sine law works for all triangles, not just 90-degree triangles. It works for those as well. All right, so first note here, the sine law works for all triangles. Works, I can spell, it's an awful R, works for all triangles. In some situations, some of you guys will just start using the sine law for right angle triangle stuff when you can, because it's the sine law. It's not like the sine or cosine or tangent law, depending on what you're given, kind of like SOHCAHTOA is. It's just the sine law all the time, which is great. But there are certain conditions. There is a condition you need to use the sine law. Because the sine law relies on having, to find out that decimal number, you need an angle and a side. The sine law requires you to have a pair, a side and its opposite angle. I call that a side angle pair. So the second note, I'm just going to make a note here to use the sine law. You must have now this is my own term. This is not a formal math term. It just rolls off the tongue easier. A side angle pair. So you have to have a side and its opposite angle. If you do, you can use the sine law. If you don't, you cannot use the sine law. We maybe need a different law, which we'll talk about another day. Okay, so that's the sine law. 2P people, you now have seen where it comes from. 2D people, we've reviewed where it comes from. Let's learn or review how to use it. So we can find sides and angles using the sine law. Here, this is clearly not a right angle triangle. Our goal is to find the distance between these two blocks, block 1 and block 2. Let's give the sine law a spin. So first of all, the sine law does work for all triangles, but do we have a side angle pair with this triangle? Do we have a side and the angle across from it? You have to think on that first. So you can nod or shake your head or whatever you think. We do not. But we're not stuck. Remember, whenever you guys have two angles in a triangle, you can always find the third. If we find the third, we will have a side angle pair. Finding the third angle should almost be just a reflex for you guys. It's not always going to be needed, but let's just do this down here. 180 minus 66 minus 52, whatever that is. 52? No. 62? Really should know this. I have several degrees in math. 62. 62. Aha. So now we have a side angle pair. How do we go about using the sine law? In this case, where there's no A, B, C, I'm going to label the distance between the two blocks we're trying to find. Use your favorite variable. I used an X, but you can use whatever you like. I'm not your dad. You could also, if you speak and write a different language or alphabet, you can use whatever you want. You can use some Greek. I know some Greek letters, but we'll just leave it as X for this one. How do we use the sine law? The sine law says, and here note, I'm using the version where my side is on top. The sine law says, if I take that side and divide by the sine of its corresponding opposite angle, which is 52, if I do that, and like your diagram could get clunky, so only add this if you wish, but maybe you want to just like have arrows indicating those are paired up and these are paired up. If that makes your diagram too clunky for your taste, then don't do it. But the sine law says that doing that division will give you the same result as if you did 2.5, that side, divided by the sine of its corresponding opposite angle, 62 degrees. That's what the sine law says. And then if you guys remember a few days ago, we reviewed how to solve proportions. This is just a proportion. Sine 52 is just some silly decimal number. So is sine 62. So we can do our crisscross applesauce and find out x just by doing our cross multiplication. Now, personally, I like to show it this way. What's going to happen is we're going to do 2.5 times sine 52 and then divide by sine 62. I just like to visualize that like this. I'll just kind of illustrate, okay, basically my sine 52 is going to be multiplied up with the 2.5. So that's sine 52, not 5.2, divided by sine 62 degrees. That would be my cross multiplication result. Multiply the diagonal, divide. And your calculators, your display calculators, some of you guys with the non-display calculators might have to do possibly an intermediate step, depending on how good you are with it. But display calculators can handle this no problem as it is. It's 2.5 times sine 52 divided by sine 62. And we've got it. The sine law is nice. It is the sine law. There's really no, as long as you have that side angle pair, and I got about 2.23 kilometers. I'll just finish this off, is the distance between the locks. The locks. Period. Yeah, the sine law is pretty slick. And as I said, not a lot of thinking involved in terms of what to do. It's the sine law. It's not the sine or cosine or tan law. It's just the sine law all the time. Pretty good. How was that? Anything you guys want to chat about? We can all use the sine law. I am supremely confident in your abilities. Now, that was finding a side. Finding sides, you can set up the same way. I don't want to do too many redundant questions with you guys. Let's try to find an angle, see what that looks like. So we can find angles with the sine law too. So this one, we're going to draw our own triangle. That's okay. When you don't have a triangle, just draw a triangle. You don't need to get the protractor out and the ruler. Just draw some random acute triangle. I'm just going to draw something like this. That I'm going to call that triangle, acute triangle TUV. So all the angles are acute. And then we'll just put stuff in different places. So I can see that angle T is 31 degrees. So maybe I'll make my smaller angle the 31 degrees. That can be corner T. That makes U and V the other sides, or the other corners. I'll just put a U and V. And then the question told me UV is 5.8. See, everything just comes from just making a decision. Good life lesson. Just make a choice and just move forward with it. What else do we have? TU is 11.1 centimeters. So we've now drawn a kind of a decent sketch of this triangle, and we have to find angle V. So not a right angle triangle. I mean, it very well could be when we do the math. Maybe angle V is 90 degrees, but we don't know for sure, so we can't use SOHCAHTOA. We need to resort to the sine law. And it's always worth asking, can we use the sine law? So you guys should just reflexively be looking for side angle pairs, because the sine law is good. So we look for side angle pairs. We got one. How do we find an angle? Here's how I would find an angle. This is just me. It's personal preference. I'm not your dad. You do what you want. But if I'm finding an angle, I like to use a version of the sine law there where the angles are on top. So I will use the version that says the sine of angle V. And I'm going to write out the sine law first this time, since I have all my corners labeled. Sine V over V is equal to, do I want to use the T's or the U's? Well, I have angle T and I have side T. If you want to label that with a T and label 11.1 with a little v. So I'll use the version that says this. Sine V over little v equals sine T over little t. And then what does this look like when we do the math? I don't know angle V, so sine V over its opposite side, 11.1, is equal to the sine of 31 degrees over 5.8. Totally reasonable for you just to plug in right away if you've seen sine law before and you're good, or if this is your first time seeing the sine law and you get it, you can just plug in right away. That's totally fine. But this is just a proportion too. The only thing is here, when we do our crisscross applesauce, and this is why I like putting sine V on top, because I'm just like last time, I just got to move the 11.1 up as multiplication. So it's 11.1 times the sine of 31, whatever that is, divided by 5.8. The only difference finding angles is that doing this cross multiplication doesn't give us the answer right away. It gives us the sine of the angle. It doesn't give us the angle, but that's okay. Divided by 5.8. Now, if you're like me here and you're writing out the decimal, keep at least 4 decimal places of accuracy to make sure your angle is as accurate as possible. I'll make a note of that. 4 decimals. Otherwise, it can impact the angle quite a bit. How do we get an angle V? I'm gonna write out what we do, but I would be totally okay if you just wrote down what V is equal to at this point. So that's our shift sign button or inverse sign button. Make sure you're in degree mode. Of course you are, otherwise you'd be getting weird answers all day. I got 80.3 degrees, which seems reasonable. 80.3 degrees. So if maybe you worked ahead and you rounded that to 0.99, you would have something pretty different actually. But with 4 decimals, we should all get about 80.3. And that's finding an angle with the sine law. Not so bad. Anything you guys want to chat about? All right, we're just doing a few more examples. I know the 2D people, you've done it before, but just bear with us for the 2P people, the first time using the sine law. So we'll do a few more things together. Can you guys try finding side x here? Remember doing this one? We did this one in the warm-up, right? That was the back of the warm-up. So the sine law should give us the same answer we got from the warm-up, just more efficiently. I am 99.5% sure we will get the same answer. Math works all the time, except when it doesn't, but it always works, unless I mess up. And then you guys are gonna try finding an angle too. So you guys do it independently. I'm gonna do my attendance. All right, if you're at home, hopefully you've paused the video and tried this for yourself. People in the classroom, here we go. So we have a side angle pair right away. So I set up my sine law, 12 over sine 60. And we multiply up to sine 25. It's the same steps every time. For those of you guys who like an algorithm where it's like, tell me what to do and I will do it, as if you have a side angle pair, it works the same way every time. 12 sine 25 divided by sine 60 equals about 5.86 meters. And that is the same value we got in the warm-up. So hopefully, again, convinced sine law works. Sine law is good. I personally don't find the sine law any more work than SOHCAHTOA. So we did things in 1 step instead of 2. So life is good. I'm going to just hang on for 1 moment or so while you guys try to find angle P. So we're finding angle P here. So we are able to use the sine law. We have the Q's. And side P. All right, I can't wait any longer. I got to come along for the ride. Sine of capital P all over. Now, I'm going to show some extra steps here. Equals sine Q over little q. And then I'll plug in. Again, if I'm finding an angle with the sine law, personal preference is to use a version with the sines on top. Just me, though. You can do what you want. Works the same either way. Equals the sine of 63 degrees over 16. If you started right there, that's fine. Good for you. To get sine P, I do 14 sine 63 over 16. That gives you a decimal. 14 sine 63 divided by 16. I usually write my decimal out. I even do this when I'm teaching calculus right now. We do use the sine law for a period of about a week in one of our units. And I do it the same way. I don't do it any differently for any grade. Now, what I maybe will do here to shorten up our steps here, I think we all understand to go from the sine of an angle to the angle, we use our shift inverse button. So I'm actually just going to go right to, okay, here is my angle. My angle is about 51.2. Did you guys get 51.2 degrees? Was I naughty with rounding? Did it say the nearest degree? It didn't say the nearest degree. And I'm a process guy. So if you rounded to 51, good for you. If you said 51.226777586, also good. All right, we feeling okay? All right, so later you guys will get a chance to grind out finding sides, grind out finding angles. Just because you did 2 doesn't mean you're pro. The 2P people want to make sure the skill's down. The 3U people want to make sure the skill's down because tomorrow we ramp things up. One last thing we'll wrap up with today is how do we solve a triangle, solve an acute triangle. So we've solved right angle triangles using SOHCAHTOA Pythagorean theorem. We're now going to solve an acute triangle. And it kind of, you guys can imagine in this question, instead of saying find angle P, this question was set up to find it directly. What if this triangle I said find side R, or find the side from Q to P? You'd have to do that in several steps, because you can't find side QP without the angle at R, and you can't find the angle at R without the side QP using the sine law. So you would have to find P first. Once you have 2 angles, find the third, and then you can use the sine law to find. I think I just spoiled the entire question. Yes, I completely did. I just literally told you the strategy but you guys maybe were checking your phone. So can you guys determine a strategy for finding out angle P, angle Q, as well as side P? I'll wait a second. We have room on the back to actually execute. But as you're thinking, with right angle triangles, often we had so much choice. Like we could pick a side, use sine, cos, or tan, or find an angle first, and then use sine, cos, or tan from that angle. It's not always the case here. Here we actually have a unique order that we have to find things in. We have no choice in the matter. All right, here I come. We have a side angle pair, which is good. It means we can use the sine law. The thing we have to find first, since we have side Q, 11 meters, we don't have a choice. Our only choice is to find angle Q using the sine law. Okay, that's the only choice. Step 1, angle Q. We also need angle P and side P. We cannot find side P using the sine law without angle P. We need angle P first. We can't find angle P using the sine law either. You have to use that old skill of using the fact that angles add to 180. Find angle P. Using the fact angles add to 180. And then finally, once you have angle P, you can use the sine law again to find side P. Now maybe you're like me and your printing is awful, so your capital P's and your lowercase p's, if you never went through that and had your nice pencil grips back in grade school, you might need to make sure you differentiate between your angle P, your side P, capital letter, lowercase letter, and then we're using the sine law here. So that is the unique. There's no other way to do it, at least with our current skill set. Okay, you guys carry that out on the back. You have room on the back, correct? You have room on the back. You guys carry it out. I'll pass around some practice. And then at the very least, just use your class time. Find a few sides, find a few angles. Like do like part A of every question. But just use your class time well. Again, the 3M people get a whole day tomorrow to do an assignment, make sure they're down with the sine law. And the 3U people, we have to take the sine law to the next level. There is more to learn. You guys did not learn it all in grade 10. Yep. We'll have like half hour practice. Jason's good today. Yep. For interest's sake, or you might actually prefer to start structuring your solutions this way. Here's an alternate way to show finding angle Q, where many of you guys are using a display calculator. So you can just do the inverse sine and then put everything in, 11 sine 61 over 12, and it will directly spit out the angle without having to write down a decimal and do any rounding. But we'll get the same answer either way. Just do whatever you feel comfortable doing. Just make sure all that inverse sine stuff is inside the brackets. And I'm going to keep, I got 53.3, which seems reasonable. Where can I squeeze this in? I'll do it right here. That means P equals 180 minus 61 minus 53.3. Whatever that is. 65.7 degrees. I got all the angles now. If you did 53 and 66, it's absolutely no problem. I'm a process guy. If you got those answers, you're clearly applying the right process. If the situation called for more accuracy, I would ask for it. But 1 decimal is good. And then lastly, we just need side P using the sine law. Equals our side angle pair, 12 over sine 61. You'll notice I don't write out the general sine law for the matching letters all the time, especially now that we've done a few. But please do that if you need to. All right, we're wrapping things up. 12 sine 65.7 divided by Sine 61. P 53.3 and angle P 65.7. Dehance, 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 dehance. All right, I just zoomed out to get everything in there. Sorry if you have to squint, but now I can just wrap up the lesson. Miss all you who are away. See you guys tomorrow.